So last time we looked at the fundamental concepts of functions, right? So we were just basically saying that, let me find my cursor here. We just basically said a function could be many different things. It could be a set, you know, we need an ordered pair. We could do an ordered pair, 2, 3, you know, just a set of ordered pairs. The first one is so the first things, this is from the domain. The second one is the range. And they're all ordered pairs. And ordered pairs, the order makes a difference. So 1, 2 is not the same thing as 2, 1. Okay, so all ordered pairs are relations. And then functions are specific relations. One input, and I can't have 2 outputs for that one. I have 2 outputs. So 1 here, 1 only goes with 2, 2 only goes with 3. If I have, you know, 1, 2, 1, 3, then I don't know exactly how, you know, which one. Does 1 go to 2 or 1 go to 3? You know, there's no rule, and I can't do the analysis. This is okay. This is certainly good as a relation. We just got a set of numbers. We can do things with them. But as far as functional analysis, it has to be 1 in, 1 output. So this is not a function. Okay, so that's kind of what we went over last time, looked at different things like graphs, you know, determining if things were from a graph. And from a graph, we use that fundamental test, the vertical line test, so that if we have some graph that, you know, we need to be able to do here, 1 input to 1 output. So this is a good function, but if I have something like this, I've got 3 outputs for 1 input. Which one do I use? Do I use that one, or that value? This is the y value corresponding when I do that. Okay. So as we go forward, most of the times we're going to be assuming that we're dealing with functions. Okay. So let me give you a few of things that we can consider functions that we're going to do analysis on. Let me do all polynomials. Okay, so I'm going to do them p of x, a to the n, x to the n. So this would be a nth, the general nth degree. So it could be a 1 first degree, a second degree quadratic, a cubic, 4th, 5th, 6th. Nth degree polynomial looks like I start with the nth. So if this was a quadratic, ax squared, and this would be generally for my b, that would just be a x. So this is the n minus 1 plus ... all the way down to, then I'll have something like a1x plus a0. Okay. So all polys, that's my short, polynomials, all polys are functions. I never run into the situation that if I take a number, do raise to a power, multiply, and adds, when I do all of this, I'm going to get a very unique number. I shouldn't come back and all of a sudden do that very same raise to a power multiplication, go through, and get a different number. Okay, so 1 input, 1 output. Now, I may have the situation that it is symmetric, like a f of x is equal to x squared, where f of -1 went to -1 squared is 1. F of 1 went to 1 squared, which is 1. So I've got the ordered pair. So this is for all numbers, but at least here we know this. 1, 1, -1 goes to 1, 1 goes to 1. It is okay for multiple inputs to go to the same output. Okay. So all polynomials are functions, and that kind of gives me a very thing, a quadratic. These are the things that we already know something about. So a quadratics are functions. If that would be n equal to 2, and linear, n is equal to 1. So this thing looks like a1x plus a0. Y is equal to a1x plus b. mx, y is equal to mx plus b, if you know that formula. We're going to look at that in just a few minutes. Okay, so a linear is n is equal to 1. Okay, so those are functions. We're going to look at others, and we'll start building up this family that we can look at, and we'll go from there. Okay, but this time we're going to focus on the linear part of them. Okay, we know a lot of stuff about linear equations, and so we're going to go over those. Okay, so once I get, before all I had was something like, and I'm going to keep it down to a linear equation, 2x plus 3 equal to 5. Okay, I had one variable, one bar, and I could solve, right? So I would go minus 3, 2x is equal to 2, divide by 2, so x is equal to 1, and that was a unique solution. Okay, but I've got two variables now, and the standard form, so there's going to be several forms of straight lines we're going to look at. Okay, the standard form of a line. Okay, and I'm not going to leave it in that polynomial. I'm going to look at that a little bit later, but here's kind of a easy way to look at this thing. Okay, I've got 2ax plus by plus c is equal to c. Okay, a and b is going to be real numbers. Okay, and then I've just got my x and my y. So usually the way this thing is you got to give me the y, and then I'll calculate. You give me the x, I'm going to calculate the y. But in this form, it's just saying that I'm always, when I'm doing this, when I'm multiplying these two, multiplying here, and I'm adding them, I'm always getting one particular number. Okay, the one good thing about this is I'm going to be able to find the x-intercepts, y-intercepts easily, okay, from that form. Okay, so let's kind of go through and kind of take a look at some of these things and see what they look like. Okay. So graph the equation and identify the x and y intercepts. This is, so one, if you're given it into this form, the standard form, to get the graph is one thing, and then basically there's another step that I'm going to throw in there, is that I want that other form of just y as some function of x. Okay, so let's kind of do two things at the same time. So graph 3x minus 2y is equal to 6. Okay, from this thing, it's the easiest to do x and y intercepts. For a straight line, so this is a 1, that power is understood 1, that power is understood 1. A n equal to 1 equation in two variables is a straight line. Okay. So what I want to do is graph this thing, and the way I want to graph it, if I've got a straight line, so that is a straight line, and all I need is 2 points. All I need is 2 points. Any 2 points determine a straight line, right? All I get is a point and the straight line between them. Point and a point, and all I do is just draw a straight line in between them. Okay, so all I need is 2 points. Why not the x and y intercept? And in this form, this is the easiest thing. So all I'm going to do is do what it said to do before. Last lecture, I said x-intercepts. To find the x-intercept, I set y equal to 0, And then my y-intercept, I set x equal to 0. And then I'm going to do a quick graph of those things, okay? So let's do the x-intercept. Set my y equal to 0, so I'm going to go 3x minus 2, 0 equal to 6. Well, that goes out. And then all I have to do is solve. Divide both sides by 3. We learned how to do that. Now we can go one particular value makes this true. X is equal to 2. Okay. So I'm going to go over here. I'm going to kind of draw very quick. All we're doing is doing quick sketches to, over on the side, learn things about what equations do in two variables, functionals, how the function behaves. You know, we're going to go to Desmos. If we need a nice, clean, crisp picture to put in a Word file for a project, we're going to go to Desmos Graph, clip it, and then go from there. Okay, so I usually do mine very quick, 1, 2, 3, you know, 1, 2, 3 for something like this. I need at least an x equal to 2, so I'm just going to go 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Use that same scale, hopefully. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay, so at x equal to 2, 1, 2, I'm going to go ahead and write that 2, 0. X is equal to 2, y is equal to 0. Here's my x, here's my y. Okay, and then I'm going to do back over here, I'm going to find my y-intercept by setting x equal to 0. All along, this is what I did, all along the x-axis, y is equal to 0. So that's why the x-intercept. All along the y, x is equal to 0, hence the y-intercept. So I set x equal to 0, I go back to my original equation, 3 times 0 minus 2y is equal to 6. Now, all of this goes out, and I'm just solving this, negative 2, and that should be negative 3. So x, you know, negative 2 here, negative 2 here, and then that's your 3. Negative 3. Okay, so down over here, I go back, negative 1, negative 2, negative 3, and I'll kind of label that one 0, x is 0, y is negative 3, and then I just draw a line through there, and I'm kind of leaning over to do this. So let me kind of use the edge of this, and hopefully this will work. So if I go right here, kind of a straight edge type situation. Okay, and I would write 3x minus 2y is equal to 6. That's my standard form in the graph. Okay. Now, for us, we are interested in functions. I want to take this and put this in the form of some function. F is some function of x, so I'm going to name this rule, but I want this in terms of some variables in terms of x. Okay, so what I'm going to do is take 3x minus 2y is equal to 6, and I'm going to solve for y. Okay, we did a little bit of that when we were doing a review of solving for particular variables. I want this all by itself. Okay, so I'm going to get everything else over on the other side. So now I'm going to subtract my 3x from both sides. So I get negative 2y is equal to 6 minus 3x. And then I want to divide both sides by negative 2. So here I'm going to have 3/2 x, negative into negative, and then this into this. So this means 6 divided by negative 2 minus 3x divided by negative 2. 3/2 x minus 3. And then I declare this as my function. Okay, so f of x, 3/2 x minus 3. That's my function. Okay, so this equation up here, I could also, this line, I could say y is equal to 3/2 x minus 3, or the graph of f of x, 3/2 x minus 3. And the reason I use this notation is to let you know, just by looking at this, is I'm using functional notation. One input, one output. Whatever the input is, I get one output. I'm using functional notation. Okay, so let me go over here. Okay, so let's move on. It's going to go back through. So here 5x is equal to negative 10. Here x is equal to, so I solve. This is all I can do for this one, okay? Negative 2. I can say at 5x is equal to negative 10, what about x equal to 0? Then that's not a valid equation. So this says that I've got some constant graph here. Sorry, 5x negative 10. X is equal to negative 2. So over here at negative 2, that's a straight line here. And all along that straight line, this is one thing we know, is that x is equal to negative 2. So the x and y intercepts, all I've got is that intercept right there would be x equal to negative 2. That would be the x-intercept. Y is equal to 0. Okay, I have no y-intercept. I can't set x equal to 0, which would be right there, and get a y output. Okay, so one more, I'm going to let you do A, and I do want to cover what B looks like, because we're going to use this. This is B, sorry. So B says y is equal to 1. Okay. That looks like all along the line, here's 1, so x equal to 0, 1 is the y-intercept. That's the only thing I've got. I've got no x-intercepts. And I write the equation of that constant line as y is equal to 1. Okay. So there are other ways. What determines, let me kind of get before this. What makes the difference of a line? Okay, so geometry, right? Geometry, I'm just going to have two lines, right? That one and that one, but they're not kind of oriented, you know. When I do this, I do analytic geometry. It's called analytic geometry. I'm going to overlay them on an XY axis with a scale, and I can do math analysis on those things, okay? So the first thing I want to do is say, well, what is the difference between that line and that line, okay? If I extend this thing and they cross, if they cross, they naturally don't have the same slope. If they have the same slope, this is what the slope is. It's kind of like if I went over here, x units from here, I went up y units, okay? This one, so if I have x1, y1, here's these units here, and I'm gonna call them a little differently. I'm gonna call them delta x and delta y, meaning the change, how high they go, how far they go over and how high. This is delta x1, delta y1. This would be, just from any points, I'm just talking about the difference going over, this would be something like delta x2, delta y2, okay? If delta x1, sorry, delta y1 over delta x1 is the very same, if I do this division and this division, simplify, if this number, so this could be like 1/2 and this would be 2/4, right? If they're the same number, they have the same slope. Okay, so same slope, but this was like parallel. So if they have the same slope, you know, parallel lines. Parallel lines would be just like this. In regular geometry, parallel lines meet in infinity, so they don't cross. Okay, so if I have something where they're not touching and I have parallel lines, same slope, these things would not cross. Okay. So let's kind of go through and determine slopes to figure out, you know, well, if I can compare two lines, I can tell if they're parallel, I can tell if they're perpendicular. So this is parallel lines. That would be perpendicular lines. That would be a perpendicular line where this is a 90 degrees or right angle. Okay. So here's the definition of a slope of a line. I'm doing this with on coordinates, so I've got, you know, I do my Cartesian coordinates, plane, my Cartesian plane, my x, my y, 2 points like I did last time, point 1 left to right, and then point 2, point 3, da-da-da-da-da. Point 1 has coordinates x1, y1, whatever this number is, I'm kind of label it with a unique x and y, a unique x2, y2. And I want to know if I drew a line through this thing, the slope would be, you know, if I drew, this line is parallel to the x-axis, this line parallel to the y-axis. So I'm finding this little distance here, that's my delta y. This distance here, I'm going to call that delta x, okay? So the slope of the line, if I go back over here, it is just, here's x1, y1, my point 1 and point 2. I'm going to start to the right to give me like positive numbers, but it's okay if I start from this, go P1 minus the P2 coordinates, as long as I stick with it. So the way this is given, and this is the general form, y2 minus y1 divided by x2 minus x1, and naturally this can't be equal to 0. If that was equal to 0, I would have a vertical line, and this slope is not defined. There was no change in x, but I had a change in y. Okay, and then that would be division by 0. Okay, so let's go through and kind of pick out, let's kind of do a slope calculation. We'll do a quick one. We'll come back and revisit them in lab. So if I've got, you know, find the slope, -2, 3, and 1, -8, okay? So if I did a quick sketch of this thing, a quick sketch, I'm just going to the side, -2 over, this is going to be between -2 and 1, -2 is be my point 1, right? Because this is further to the left. So somewhere like this would be -2 and then 1, 2, 3. So somewhere like there. And then 1, -8. 1, -8 would be 1 down here someplace. 1, -8. -2, 3. Okay. That would be that point. It looks like it's a 3, but that we're just going to kind of go here, put a bigger point there. Okay. And so if I drew a line through there, again, I'm just going to kind of use this edge here and say through there, what would be the slope? Okay. So here's my P1, my P2, Y2. So I'm going to do the slope calculation. My M, I'm going to use M a lot. That's kind of, and we're going to see that float up in a little while. Y2 minus Y1, X2 minus X1. So that would be, I need to make sure I've got my signs. This is my Y2. So I'm going to have -8. We'll put that in little parentheses like that. Minus Y1, which is 3. Divided by my X2, right? This is my P2. would be my 1 minus my negative 2. So I want to make sure I've got those signs, so if I've got a negative, this becomes there. So negative 8 minus 3 minus 11. 1 minus and a minus is a positive, so that's a third. And that's the slope. The negative slope, m is negative. That means I'm decreasing from left to right. M is positive. I'm increasing left to right. Okay, so let me continue. Do the same thing, do the same thing. Find the slope of the horizontal line. The horizontal line, the slope would be 0. I have no change in y, and any two x's you pick for a horizontal line. Okay, a vertical line has an undefined slope. So I've got x is equal to negative 3. Y can be two values, but the x's have not changed, and that's division by 0. So that slope is undefined. Okay. So here's a general. Here's your positive slope. Here's a negative slope. And again, I'm not going to kind of do it with this. I want to do it in a different form, and we're going to talk about that in a minute. So horizontal line, y is equal to k. K is a constant. I have 0 slope here. Here's a vertical line. X is equal to k. K is a constant, so x is equal to 3, negative 3. Undefined slope, because I haven't, without a change in my x, I've got any two different values of y. Okay. So that was kind of based around the standard form. However, the slope really goes with the slope-intercept form. So I'm going to go ahead and introduce that. So this is the slope-intercept form. This is the most useful. This is the most useful. In terms of what we're doing, functions. Okay, it was easy to graph that standard form, x equals 0, y is equal to 0, give me the 2 points, and I draw. But here is the most useful as far as looking at the equation. So this kind of should have you thinking of, this looks like f of x is equal to, okay, mx plus b, okay. But in this form, these two forms right here, the m is what we had been calculated as the slope. This determines how fast or how slow this thing is going up. And this is the y-intercept. Hence the slope-intercept. Okay, slope-intercept. Okay. And the way I say this is the y-intercept, why is that the y-intercept? So if I set x equal to 0 like we always do to do the y-intercept, this would go out no matter what the m is. This is going to go to 0, and I'm just left with y is equal to b. So 0b is that intercept when I graph all along the y-axis. All along the y-axis, x is equal to 0. So somewhere out here, 0b is where it crosses the y-axis. Okay. So write the equation in slope-intercept form. Use the slope and y-intercept to graph the line. So this is kind of a little differently. Why don't I just go ahead and say, well, so this is where we started with 3y minus 2x is equal to negative 6. I kind of did that one a while ago, so that's okay. So let me go here. Let's start with this one. X is equal to negative 2y plus 4. I want to solve for y. I want y is equal to mx plus b. So take this, turn it into this form. That's what I want. So I want to solve for y. So leave that alone. Get everything else over on the other side. So minus 4 is negative 2y. Divide by my negative 2. Cancel. And I'm going to write this over here because I like this left to right. This into this into that. Minus 1/2 x, or minus x over 2, whichever you prefer, plus -4 divided by -2 is plus 2. Okay, so a slope of -1/2 b is equal to 2. Okay, which means if I were to graph this, I would start at b is equal to 2, so 1, 2. So that's where I would start at on the y-axis, and then I would do the slope over. That means for every x I go over 1, I drop down -1/2. So if this was 1, by the time I got here, I would reduce by -1/2. So this is 1, 2. Here's my 1. If I went from 0, my starting point, step over 1, because look, this is what we're doing, delta y divided by delta x. So if this was 1, I'm dropping down my y value that I've dropped down is just that -1/2. So now that gives me a second point. And then if I'm careful over here, that would be my graph without the x-intercept. But that's kind of what I'm doing. This should be here and here, but that's okay. Okay, and then I would just say, if I'm using functional notation, I would just go f of x is minus 1/2 x plus 2. And I've just graphed it with just basically this. Give me the starting point, and then if I know if I go over 1, then this contributes minus 1/2, so I would have gone down 1/2 from 2. So that's 1.5 is where I'm at here. So this would be x equal to 1, 1.5, or 1 1/2. Okay, so let's continue on. If I went here, let me kind of put all of this stuff together. So write the equation and do just the y-intercept, use the slope of y-intercept, so I didn't do the x-intercept here, but I could do the x-intercept once I get to here by setting, so here I would want to actually put y is equal to 0 and use x is equal to 4. So that would have been easy. Sometimes I kind of go back and say, well, where's the easiest to find? Well, here would kind of be the easiest. If I set y is equal to 0, I'd have my x equal to 4. I don't want to go back over here and set y equal to 0 and then solve again. It would just, that's just too much extra work. Okay, so I think we can do all of those. Okay, so here is the next thing that I want to do is say, I'm giving you certain information. And in this case, I've got a write an equation of the line in slope-intercept form. So what it's saying, it wants something in this form. And naturally, I could write that later on in functional notation, but it's easier just to manipulate with y here. Okay, and I need the point, so I'm given a point that it passes through is -2 and 3 and has slope m equal to 5. So if I kind of go here, and I pick a point, -2, 3, so if this was like -1, -2, 1, 2, 3, over, so here's my point, -2, 3, there's a bunch of lines that could go through that one point. Only one point, man, there's like an infinite number of lines that's going to go through that thing, all of those, okay? So it's saying it wants a particular one with slope m equal to 5, which means if I go over 1, I go up 5, okay? So here, I'm using the information that I'm given. I don't know what my b is. I do know m, so I'm going to start out, but then I'm going to use this point that it passes through and solve for b. So this is what I do. So my step 1 for this particular situation, I would say, okay, well, my y is going to be my 5x plus b. Okay, that's given. And I also know that it goes through negative 2, 3. This is the x, this is the y. So for here, I know this is 3 when this is negative 2, but I don't know what b is, but I can now, everything else is well defined, and I just solve for b. 3 is equal to negative 10 plus b, and then I add 10 to both sides. 13 is equal to b. And then I just rewrite. Y is equal to 5x plus 13. At negative 2, 5 times negative 2 is negative 10 plus 13 is 3. Okay, but now I know what my y-intercept is 13, so way up here, right, way up there. And like I said, as we were doing the slope was 5, every time we go over 1, we go up 5, go over 1, go up 5, okay? So 10, by the time we stepped over 2 to get over here, we increased by 10, and the 10 plus the 3 would be the 23. I'm sorry, the 13. The 10, I'd go over 10. Go over 5, then another 5 is the 10, and I'm at 3, so I'd be up at 13, and that would be the y-intercept. So this thing goes up pretty quick like that. I would use this bottom thing to graph. So again, let me kind of go over this thing to get the b. I use this point, the negative 2, 3. I know it goes through, it's given that it had to go through negative 2, 3. So my y value is 3. My x value is negative 2. So there's my negative 10. And I'm solving for b. So I'm adding this negative 10 I'm getting over there, adding 10 to both sides. So that lets me know that the b is 13. Okay. So this is going to be, for my little quick sketch, I got to go up to 13 here. I can also go back this way and do my x-intercept. And my x-intercept, so let's do the x-intercept instead. I'm going to set my y equal to 0 and solve for x, okay? So 0 is equal to 5x plus 13. And if I get negative 13, then divide by 5, I get this is negative 13 over 5. Negative 13 over 5, comma 0. Minus 2 3/5. Minus 2 3/5. So this would actually be pretty close over there. Okay. So write an equation of the line that passes through the point and has slope equal to 3. I'll do the very same thing again. So I'm not going to put it on over the graph or anything. I'm just going to write it. So y is equal to mx plus b. I'm given m is equal to 3, and it passes through this point, negative 1, negative 4. So my first step is to use this, and then use this as my x and y. So this is my y, that's my x. So negative 4 is equal to 3 times negative 1 plus b. That's what I don't know, and then I just solve. So negative 4, 3 times negative 1, that's my negative 3 plus b. And now I get that over there by doing plus 3 plus 3. So negative 1, this goes out, is equal to b. So b is equal to negative 1. And now I get to write my equation, the 3x minus 1. So we just did this. It's just a different name and a different way of doing it and a different way of defining it. The slope again, the slope is what they're talking about here, but I'm going to use a different terminology once I go. The slope, this is the slope, is equal to delta y, delta x. This is the change in y divided by the change in x. Okay, the slope of the roof, right? You got a rooftop. Here's your house. It's a poor house, but that slope, the pitch, the very same thing. It's all the very same thing. Okay. This is also, but what happens? So here's the thing. So here, I got this. If I've got a straight line, I've got no problem. There's my delta y. Here's my delta x. I calculate everything is fine. And no matter which 2 points, for a line, m is constant. I got no problems. I can calculate it. It stays the same. I can use this big point. Now delta y, delta x, it always reduces down to the same number. Okay, but here's the big but. What about if I have a curve? Okay, that general, I've got a function. I'm going to do a function because it's not going to wrap back over on itself. So I've just got a general functional curve. Okay, and this is the way we kind of notate this. I've got some curve, but it's a function. One input, one output. I just say y is some function of x. Okay, and this means that this is some rule, x squared plus 2x plus 1, right? That's what that kind of indicates. I don't know what the rule is. It's just here's some general picture of a function, okay? I would never do this and say y is some function of x. Why not? Because it fails vertical line test, okay? There, okay? So I start out with here, and then I'm going to say, well, what's the slope of this? Right, if I pick 2 points like here and here, I get one value for my slope, delta y, delta x. Okay. What about if I pick this point? Then I get kind of this line. Here would be that line, that would be the slope. If I did here, I've got another line. This is a different slope. For curves, general functional curves, the slope is not constant. The slope is not constant. Okay, so what I need to do is do this thing that's like the average slope. Okay, average slope. Okay, so I'm going to kind of do this thing, and I'm going to call it the average rate of change. Okay. So the average rate of change, average rate of change. I'm not going to do anything different, but I have to tell you over what 2 points, okay? So I've got to have, if f is defined on the interval x1, x2, then the average rate of change of f on the interval, this is the slope here. And they call it the secant line, but the tangent line is just really touching. We're going to talk, you'll talk more about that in calculus, and I might talk about it a little bit later. The difference being, here's my general curve. That would be the tangent line. Let me kind of round this over. The tangent line. I just touch it at that point. Okay, and a secant line would be that, between point 1 and point 2. Okay, so the average rate of change, and this thing a lot of times is shortened to the arc. Calculate the arc, the average rate of change. Okay. And it's the very same thing as the slope definition, but here I've got to give you y2 minus y1, x2 minus x1. I've got to give you the points, and then you've got to calculate it by doing this kind of definition. M is equal to the value of the function at x2. So this is basically the y2, right? But I'm just giving you the point given two points, x2, y2, okay? and a rule, and the rule, okay, I evaluate the function at x2, that gives me y2. I subtract off the value of the function at x1, which gives me y1. Okay, that's just kind of those. I can give you these two numbers and the functions, or these, I can use these two things. And then x2 minus x1. Okay. So for this, I would give you the rule and just here's x2 and here's x1, and then I evaluate these to get this. If I'm given these 2 points, I can just use the y2 and the y1. I've already been given that. I don't have to recalculate these things. Okay. Here is the general curve. Y is equal to f of x. I'm given some rule, and then I plotted it. And this is kind of the shorthand notation of a general curve. Here is a point x1 and the value of the function at x1. Because if I evaluated it, that would be where this thing crossed. Here would be x2 and the value of the function at that x2. That would be the f of x2, the y value here, the y value here. And the secant line would go through there, and that would be the slope of that line when we calculated the average rate of change. Okay, and here I'm just calculating y2 minus y1, x2 minus x1. So these I'm given the points. Okay, and then I've got a graph. Now here's the one that we really need to calculate. Okay. So I've got a f of x is equal to x cubed plus 2. And I want to calculate the arc from x1 equal to -3, x2 is equal to 0. In general, this is given like left to right, x1, x2, x3, okay, but you only need 2. So I need to calculate the value of the function at x2, which is f of 0, and f of 0 is just, by that rule, for this particular one, 0 cubed plus 2. So f of 0 is 2. F of x1 would be basically my -3 cubed plus 2. -3 times -3 is plus 9 times -3 is -27 plus 2, and that would be -25. Okay, so my arc would be my f of x2 minus my f of x1. My x2 is 0, my x1 is -3, and that goes like that. Okay, so it would be 27 thirds is equal to 9. That would be the slope of that secant line, and I could then find an equation of that line because I know the slope and the points that it goes through. Okay, so the points would be, here's the first one, 0, 2, and then it would also go through -3, -25. Okay. Okay, so here we'll kind of spend a little bit of time on that later. This is kind of the main thing, is getting the function going. We'll learn some more about this coming up later. Let's see, make sure we've got everything. And I think we're good for that, okay? So I'm going to hold off doing the rest of the stuff until later, and I'm going to stop recording.